Hi. Throughout this talk, I'm going to tell you how to use the cock-proof assistant to generate fast code for field arithmetic. But first, let's take a look at how it is done today. It is quite common for field arithmetic to be implemented from scratch for each modulus and separately for 32-bit and 64-bit CPUs. At the very least, each modern web browser includes implementations of the P256 and Cryptographic elliptic curves and the underlying finite fields. This duplication of security-critical code has led to a good amount of concern amongst cryptographic library maintainers about how to make sure that all of this is correct. And let's just look at a concrete example of how this plays out in the field. This is a recorded conversation on the OpenSSL bug tracker, and everything starts with the studious user noticing that some comments in the source code are not entirely accurate. In particular, some integer overflows that are not supposed to be happening are in fact happening. Quickly, a counterexample is produced, and some contributor points out the paper that shows how to attack a similar bug in a different implementation. Of course, nobody has time to actually see whether the attack is applicable here, so people just propose some patches, fix them up, and only after a couple of iterations later, the patches are committed with a ringing endorsement that they passed 6 billion random tests and there are no low-hanging bugs left. What we do is rather different. We write one implementation for each general algorithm for module reduction. We use compile time specialization to generate code that is quite similar to what an expert would write. And we prove each implementation correct in cock, once and for all. So with one proof applies for all compile time specializations and all runtime inputs, including those not included in the 6 billion. And this last feature was convincing enough that the maintainers of BoringSSL replaced some of their handwritten implementations with our generated code, even though at the time it came with a slight performance penalty. It has now been fixed. I will show you a concrete demo of what our framework looks like from the cryptographic library maintainer's perspective. You start by specifying the implementation strategy, the name for the code. This is not relevant to what actually gets generated, the number of digits to use per field element, the modulus of the finite field, and the number of bits in the multiplier input for the CPU, and the operation you want to synthesize, and out comes code. In fact, out comes quite a bit of code. And I am quite glad that I was not the one who had to write this out by hand and have the opportunity to get math wrong in it. And it runs as fast as expert-written code. It is essentially the same code, just generated by a tool. So the performance difference is a tiny fraction of the overall execution time. But it is still much faster than using a generic library that uses a generic algorithm at runtime. However, specialized assembly code is even slightly faster than either expert-written C code or our C code. And this picture is essentially similar for other elliptic curves as well. This here is curve 24519. The key difference that makes specialized implementations fast is that the implementer gets to match the representation of field elements to the modulus in question. For example, with 64-bit integers, we might represent the 256-bit field element using 4 digits. And this way, the weight of the 5th digit, hypothetically, would line up with the modulus. 2 to the 256 is quite close to 2 to the 255. So this enables speeding up module reduction. However, splitting up the digits in an unconventional manner can give even bigger speedups. For example, if we have a 127-bit field element, we can split it into 3 digits without using all the bits in each of the registers. So one digit gets only 42 bits, the second one also gets 42, and the third one gets 43. So it's not even a normal base system. There are different numbers of bits in different digits, and yet this ends up being faster because it matches the modulus closer. 2 to the 127 is very close to 2 to the 127 minus 1. And the key challenge in our library is to figure out how to encode the algorithms of modular reduction in a way that they can be used on multiple representations. And fixing the representation at compile time should give us back the code that an expert would have written when they would be writing an implementation using that same representation. So this is the overall architecture diagram of our library. All of our code is written in the cock-proof assistant, and we do make heavy use of it. It would be non-trivial to replicate in a different environment. The specification of each operation is rather simple in terms of cock standard library, integer, big num functions. And each generic algorithm we write is proven correct against that specification before any specialization takes place. Now, the demo I showed you earlier had some expert-chosen parameters that were fed into the code generation, and these are irrelevant for correctness, but of course, if you pick wrong values, the code will be slow. And after the parameters have been specified, we have a certified compiler we built and proved correct in Coq that takes the generic code and the parameters to produce specialized code. The focus for today will be the generic algorithms for finite field arithmetic that we extracted from examples of expert specialized code and that we have not seen presented in this general form before. However, we will walk through an example of how this code gets compiled to specific C code as well. If you are interested in more details of the compilation pipeline, these are present in our paper. At the center of our library is a compile-time representation of field elements, which is somewhat similar to the grade school positional representation, but there is a key difference, so please pay close attention to this slide. Each field element is represented as a sum of products. So there's a list. The list contains weights. This is the left part of each pair, and digits. That's the right part. And one field element can be represented in many equivalent ways. For example, here we break up the number 876 into 5 digits, even though it is only 3 digits long normally. And the first digit is of value 4 with weight 200. The second digit is of value 5 with weight 10. And then there's a third digit, also with weight 10 and value 1. And then there's a digit with value 16, even though it is placed at just weight 10, and even though weight 10 is separately present and 16 is at weight 1. And this is allowed in our library. At compile time, representations like this might occur, and this, in fact, makes it significantly simpler to implement some of the fast tricks for modular reduction. Here is some example code that uses this representation, and it is not a toy example. This implementation of schoolbook multiplication was actually used in the demo that I showed earlier. It's 4 lines of code. The proof is also on the slide, even though it's grayed out, and I do not recommend trying to read it, but it's that short. Let's instead look at the example on the right-hand side of the slide. The input is 2 numbers. One of them has 3 digits, the other has 2 digits. And this implementation generates the table of partial products, as we all learn in grade school. And it does not even compact the partial products. So if there are 2 partial products with weight 10, multiplication just leaves them as is. The deduplication step will be performed later, and the detailed implementation of that is actually more general than what we see here, so we do not get to that yet. However, it is not obvious how fast this code would execute, because looking at it naively, it looks like it might use dynamically allocated linked lists and perhaps even big numbers to represent the individual digits. So we'll need to step by step get rid of those concerns. First, let's get to straight line code. So we will need to unroll this loop, and we want to have, for the values of the digits, which I'm not sure my laser pointer is actually pointing to, we will have, instead of 18 here, we would want to have a symbolic expression in terms of input variables. And Coq has this great built-in functionality called CallbyValue Evaluation with a blacklist, so we can just specify which functions we do not want to be unfolded. And in fact, we go in and we find this implementation and see, at this syntactic location in the template represents runtime multiplication, and we just insert the wrapper definition there. So that star is now different from the star on the left. And then we call CBV with the runtime multiplication in the blacklist, and here is a specialized version for 3x3 digit multiplication. Now, we're not still all the way there, because even though there's a digit with weight 1, there are multiple digits with weight 10, and even 3 digits with weight 100. And what we would like to have would be 1 digit per each weight. However, the problem is actually slightly harder than that, because not only do we want to get rid of duplicates, we want to have digits with compile time known weights. So if your crypto library outputs a 5-element array, you would expect that this array represents a number in the manner that the first digit has weight 1, and the second one has some known weight, and the third one has some known weight, and you don't want to need to look up at runtime what those weights are. So instead of deduplication, we actually need to perform an operation that gathers the weights that are desired in the output and does something with the weights that are in the input but not in the output. So for example, if the input contains a digit with weight 500, but the output-based system only contains weights 10, 1, and 100, we need to do something with that 500 to get rid of it. And we could rule it out. We could say our code should never generate this, and therefore it's OK if we don't handle it. But we tried that, and it was a lot of work to rule it out in our proofs. So instead, we supported it. And turns out there is a nice way to support it. Simply to place the value x at weight 500, you multiply x by 5, and stick it in the hundreds pile. Proof is very simple, and furthermore, it actually adds more power to our library, as other algorithms don't need to pay attention to what weights they generate in their output. On this slide, I have listed 3 famous tricks for module reduction. So the first one is pretty old, at least a couple hundred years. The last one is from 2004. It was introduced in the paper that introduced curve 25519. And all 3 of them rely on this insight that if your modulus is close to a weight that appears in the PACE system, then it is possible to speed up module reduction. The way I like to think of this is that if the modulus is only c away from a power of 2, then that power of 2 is congruent to c in the field in question. So we can perform module reduction by just replacing the power of 2 in question with c. And c can be an arbitrary field element. It might consist of multiple digits, or it might just be 1. And in fact, these 3 tricks are all the same so far. The only difference comes in how you represent c and which cases of the deduplication algorithm get triggered when gathering the digits for the desired output weights. Now, I'm going to jump into a rather large example, which we'll dissect step by step. But first, all the steps that we're going to dissect. Sorry. These steps represent the parts of the demo I originally showed. There is no other code than what is described on the slide in producing the C code that was on the black screen. So the module multiplication starts out with the 2 inputs and the module reduction coefficient c in associational representation, as described earlier. We use schoolbook multiplication, whose code was on the slide. Then, to perform module reduction, we find all weights divisible by 2 to the k, which is congruent to c, and replace them with a schoolbook multiplication by c. This step works one weight at a time, and again, is very easy to prove correct for this reason. And then we just run deduplication. And the deduplication actually has to done quite a bit of work, at least in the case of curve 25519. Most commonly, it will replace weights of the form c times b, where c came from module reduction, with digits of the form c times x at weight b, because probably c is not present in an output list of desired weights. And for this to be fast, c and k need to be picked in a clever fashion. There have been quite a bit of study about what are good values of c and k, but for correctness, it's irrelevant. If you put in bad values, we get slow code, even though it is technically still correct. This picture is our generated code for curve 25519 on 32-bit machines. And the same picture has also appeared in several papers discussing implementation of curve 25519 in handwritten code as an intermediate result on the way to the final code. We will now explain the different coefficients appearing in this figure in terms of our deduplication algorithm. First, the entries below the diagonal have a factor of 19 in front of each partial product. This is there because reducing 2 to the 255 modulo 2 to the 255 minus 19 gives you 19. And since there is no weight with, say, 2 to the 26 times 19, instead, the value of the partial product is multiplied by 19, and the weight 2 to the 26 gets used. Further, there are some prefactors that have nothing to do with module reduction at all. In this checkerboard pattern, we see values at either odd or even indices have a prefactor of 2. And this is because the underlying base system uses a non-uniform radix. So the first digit gets 26 bits, the second one gets 25, and so on. So when you multiply 2 digits at weights 2 to the 26, the resulting weight is 2 to the 52. But the positional system only includes the weight 2 to the 51. So the value of the digit gets scaled by 2 to compensate for the lack of the factor of the 2 in the weight. And these happen to appear in this checkerboard pattern that I believe has also been independently derived, but in our case, we don't have to. As the final step before calling it done, we need to assign fixed width integers for each intermediate result, because so far we have been working under the assumption that each digit is represented as a big num. However, this is actually pretty simple. We simply guess some values within which the inputs lie, and then track the bounds throughout the code, adding up the upper and lower bounds as they accumulate until we reach a bound on the outputs. And there's some carrying step, which I'm not covering here, but is covered in the paper and is proven correct, that then reduces the values of individual digits to within their starting ranges without changing the value of the field element. Now, the thing that surprised me the most about this project was what took time. In the beginning, we spent several months working directly in the positional representation, And we did manage to prove the first one of the 3 module reduction algorithms that I showed. And it was still not quite complete because there was a case that it didn't handle optimally, and we were rather dissatisfied with it. And then we just essentially happened onto the associational representation, and everything suddenly worked out. In fact, we had already implemented the second 2 algorithms by the time we started to consider them. Some time was spent trying to get the Coq built-in partial reduction to evaluate fast enough for our purposes, because Coq has normally been used for pure mathematics, or at least abstract study of algorithms, and big terms are rarely encountered. And the same pattern repeats for other algorithms that I did not cover today. Our library includes Montgomery reduction. It first took us more than a week to find out all the necessary invariants for proving Montgomery reduction from various pieces of literature discussing it. But once we got it, we at one time decided to nuke our library and rewrite it from scratch, and it took only a couple of hours to do the proof based on pencil and paper notes we had made the last time. Overall, as for the technical deliverable in this project, I am pretty satisfied with the shape of the code and the proofs. They're surprisingly simple. I would feel OK comfortable assigning some of them as homework assignments in an undergraduate introductory class to Coq. It is pretty cool that we can use one implementation for multiple primes. And the performance is pretty good. It is, in fact, as good as experts can get while writing in C. Of course, it could be better if C compilers did a better job of register allocation and instruction scheduling. Maybe one day, but not a part of this work. And of course, if Coq was built for a compiler execution environment, it would have run faster for us, but so far we managed. Thank you.
Thank you very much. And thanks for staying inside the time window. Any questions? Can you please come up to the microphone? No questions at all? I guess they're still all digesting. Do you want to tell us anything else that using the 1 minute you have extra?
We also proved correct some elliptic-curve algorithms using this library, but fortunately it did not fit in this paper, so maybe one day we'll talk in a separate context.
OK, well, thank you very much.